Hi, I'm Rajesh Jayapal. I'd like to take you through to give an understanding that AI is an optimization problem. As I mentioned, AI is an optimization problem, and the, the scope what we have is to find the target y given the equation f of x. So f of x defines the input features that can be used to find the target y. Take for example a simple equation weight which is equal to the coefficients b0 plus b1 into height. And I'm giving you a very simple data set, and I would like you to uh, find the coefficients b0 and b1 using the provided data set. Just think about it, and I would like you to take a quick 10-15 seconds and keep the answers on your mind, and we'll try to understand how that has been approached, and how the system kind of approaches this, and what's the kind of optimization that happens. So can you give it a try now? Okay. Can I assume that you have defined the coefficient of B1 as something like 5? Okay, we'll take that. Suppose if B1 is 5 and let the height be 180, uh, that's not working well. Probably can we consider B1 as something like as zero point 0.5? Yeah, if it is zero point 0.5 into 180, that is something close to 90. Yeah, that looks something very close. Now check with this particular data. Height 3800 and B1 is zero point 0.5. No, we are missing up something. How about with this data? Height is 150 and B1 is zero point 0.5. There also we are kind of missing something, right? Yes, but ultimately, this particular activity gives us an understanding that how we have approached in terms of finding the value b1. We start with a random value and then try to apply that with the data that has been provided. Once we feel that something is working out, we try to apply that with an unseen data. In this case, it is 200, weight and height 3800, and we found that it is not uh, yielding the result what we were looking for. So basically, what this indicates is this is how basically, like as a human, we are trying to define the coefficients of b0 and b1 by taking a random value and then try to kind of optimize that to a value which is very closer to get that particular target y, which is equal to f of x. Now we'll try to understand the definition of optimization. So optimization by definition clearly says that the goal, the objective is basically to find the the function which provides the loss which is minimal, and the function which provides the accuracy which is quite maximum. And of course, we need to have some sort of constraint included to achieve this, right? So in this particular scenario, the goal is very simple. We will see the constraint part at the later stage, but we'll take the loss, the core objective of optimization is minimizing the loss, right? So now when we say that we are trying to minimize the loss, as we like as we saw earlier, we take a random value and then we try to come to an optimal value which we feel that it's something is what we are looking for, right? Now assume that you are on top of a cliff and your objective is to come to an optimal valley. and the decision you take to reach the optimal valley is what defines how the in what way you are approaching that particular the steps to reach the optimal value. So the graph what you see here clearly shows that there is a global maxima, local minima, and there is a kind of a local maxima and a global minima. What this defines is the feature, the data points what is provided to us, right, that has a behavior of this particular nature. And this clearly indicates that the optimization path that we are trying to take, it is not a straightforward one like we are climbing down from a cliff and then directly reaching a sub optimal valley. So, considering the machine learning, the complexity of the data, no, we have to go through this, no, many local minimas before we reach the optimal, the minima, which is called as a global minima. Okay. So, what it means is there is a tendency to kind of reach a local minima and then kind of say that okay, we have reached the optimal value what we are looking for, right? So now that is the kind of an the optimization that happens internally to understand is it a local minima or a global minima. While this being still a research problem in terms of identifying the optimal value that you have reached is of a global minima or a local minima, there are various ways you can kind of overcome such challenges to kind of reach the global minima. So that is what that defines that okay, kind of a learning rate is a parameter that is used in the machine learning which helps you to kind of optimize that path. The learning rate, if it is too small, as you see in the image over here, if it is too small, it is the closer that red dots what you see. You take a smaller steps from the cliff, top of the cliff, to reach the valley. So what happens is you are trying to kind of learn the each steps, and and you may have to come across various suboptimal planes. That in this case it's a local minima, and as we know that there is a challenge with differentiating between local minima and global minima. We need to find a way to avoid this local minima, and what's one such thing is probably by increasing the learning rate to a little higher value and see the feasibility of overcoming such the local suboptimal values. So here is where the kind of a control given to you. If you take the learning rate as a minimal, you are undergoing the each and every data points, and which also means you are kind of overfitting yourself, which you may not be able to generalize later, and also the probability of getting into a suboptimal local minimas. And on the other side, if you take the learning rate a little higher values, you may overcome the challenge of the suboptimal values, but there is a probability that you are not kind of covering the required path to reach the optimal value. So it's kind of you will be end up having some sort of a underfitted model, right? So that is a kind of a balance you have to take in terms of kind of reaching the optimal value. And from the mathematical way of looking into this is basically how we define that this is a local minima. It is basically y is equal to f of x. Take a first order derivative, dy by dx, and then try to take the second order derivative d square y by dx. And if the second order derivative shows that it gives you a negative value, that shows that you are climbing down from the peak to the negative direction to the lower one, which means you have reached some sort of a maxima and you are trying to come down to the minima. So internally, our high school max of the maxima and minima finding the maximum minima through the second order differential equation is what is kind of is applied. And the other aspect what we need to keep in mind is the nature of the behavior of the function. Okay, so that's something which I have mentioned as a convex, and the non-convex nature. And primarily the machine learning data set falls under the non-convex nature, which means no, you may have to undergo these challenges of the suboptimal values. So this is definitely for our understanding that okay, what kind of data we are dealing with. And for your understanding, the machine learning data points, most of them falls under the non-convex nature. And the question comes, how to deal with it. Is it possible to convert the non-convex function into a convex function? And that's something we will try to understand down the line. And this is the representation of the convex and the non-convex function behavior for the multivariable data points. And clearly it shows that the non-convex nature is quite complex. And it is quite difficult to find an optimal value for a function of no nature, non-convex nature. This is taken as an algorithm to quickly understand the optimization that happens over there. As I mentioned, no, AI itself is an optimization problem, and what we have seen so far is kind of from the no reaching the no the optimal value no, by kind of overcoming all those suboptimal values. That is technically defined as a no stochastic gradient descent, right? And so similarly, when you take an SVM as an algorithm, the support vector machines, from taking the binary classification as a reference, the optimization basically happens in terms of the hyperplane, that is a green line over there, defining the line, the best optimal line, which provides a maximum distance between the data points which are kind of at the boundary. So now if you consider this as a binary class, a class of yes and no category, right? And the yes data point and the no data points, how well they are separated. Okay, so the defining that no boundary is what is basically the role of the support vector machine algorithm, right? The data points which are closer to that green lines are called support vectors. And and so this shows basically kind of a ideal scenario. But if you see generally, like now the complexity of the data set, and it is not always linearly separable. And as no, so shown here, you cannot uh, define a plane no kind of directly by for data points of no plotted of this particular nature. So how we are going to approach this, right? So here is again, you move the data points from the lower dimension space to the higher dimension space, which helps you to linearly separate the data points. So the points plotted in the x and y direction is now kind of is plotted in the three dimension x, y, and z. And here you can clearly see that the points are kind of linearly separable. So this is what basically happens when we say that SVM kernel like is being used. And the kernel level optimization, the role of SVM kernel optimization is basically moving the data points from the lower dimension to the higher dimension. And obviously this high school max basically that's behind this is find the distance between the green points and the red points. It's basically the projection of point A on on point B, which is something which we have studied in our high school max. And similarly, when it comes to the recommendation engine, we will quickly understand the kind of optimization that happens. And the recommendation engine flows similar to the AI model pipeline, where you kind of collect the data, process it, and fit the algorithm, validate, and it goes on, right? So now, similarly, you know the data collection is involved, and from the recommendation engine perspective, we need to keep in mind that we have two ways of collecting the data. One is we call this that as an explicit data collection, and another one is the implicit data. So what explicit data mean is, as a user, while we log in into a retail portal, now we tend to rank or give feedback of a particular item as a user. So those things are all basically called as an explicit data. We try to try to kind of give ratings, right? So then what the implicit data means? Implicit data shows basically as a user, how much time we are spending in terms of going through the portal, and where we are what item we have selected and clicking, and going through that. So this is something the order history, and the search history, the number of clicks, right? These are some of the things which is kind of tracked, and that is used to kind of give the recommendation for the particular user. So now we need to understand from the optimization perspective. And of course, I encourage you to read further about the different ways of filtering the data, the content based filtering and the collaborative filtering, which gives you the idea about how they are making use of this to build the recommendation engine. And from our understanding perspective, optimization perspective, this is what we need to keep in mind: the explicit data and the implicit data. Now I'm showing you the rank matrix. Basically, the user, there are four users, and there are basically five movie items, and they have ranked it. And I think in this scenario, can you give a guess of what would be the rank that would be given by that user for that movie M4? Yeah, it's pretty straightforward. Why? Because it already has a pattern, and here we can kind of say that the rating would be 3. And take this particular rank matrix. How about now? Here also it is little straightforward. Definitely this gives a pattern that the user 1 and user 3 behavior indicates the same behavior, and hence this particular rank for the user 3 would be giving 1 rating. That's something which we can kind of know clearly we can understand. But consider this particular rank matrix. Here's where the challenge comes. Why? Because not every user will give a feedback or rank the thing, right? So that's basically we will get a sparse matrix. And this building this matrix is quite interesting. How do we approach this? What is the optimal way of doing it? That's what we will quickly understand. And the answer to that is matrix factorization. And again, it's all our high school mathematics. Matrix factorization, like any other factorization, 5 into 6 gives us the 30. Similarly, the rank matrix, what we have to build has to be split into this and that. Okay, and you bring back that convex and the non-convex nature of the data points earlier, right? So here clearly this is what we have is a non-convex nature of the data points, and the approach what we are going to take is converting the non-convex into a convex nature for no easy computation. Now you take this rank matrix, which is no, for 5 movie items and for 4 users. Now how we are going to split this? Okay, the first split is going to be based on the user factor. So we need to create a preference matrix for each user. So the preference matrix is based on some features. So here is where we have to optimally select how many features has to be selected. Okay, so now in this case we have taken two features for the movie item. There might be number of features like the hero, heroine, and the nature of the movie, right, and the story behind it and stuffs like that, right. So now on that aspect we have just selected two features, comedy and action, and user one has a preference of one for comedy, and for action it is no, kind of a dislike, the zero over there. And similarly you build on another matrix, basically an item factor, which talks about for that particular item, in this case a movie, M1 to M5, the ranking for those features. Okay, so now as you see over here, the dot product of the two matrices gives us the rank. Okay, so it is basically user 1 comedy is 1, and movie 1 comedy is 3. So it is 1 into 3 is 3, plus similarly for the action it will be 0 into 1, it will be 0. So 3 plus 0 is 3. Okay, so what I'm trying to say here is factoring the matrix involves creating two matrices. One is a user factor based, another one is an item factor based, and the dot products gives us the rank. Now this looks pretty simple and straightforward, but how to do it, that is a question, right? You remember the standing on a cliff and we are trying to come down to an optimal valley. The same thing has to be applied over here, where we define a random number, no, like to the preference, the user factor, and similarly for the item factor. Okay, and in this case, see, randomly I've taken zero point 0.3 and zero point 0.6 for the comedy and action for the user 1, and for the movie 1 it is 1.4 and 2.5. Now if you do the cross product, we get M1 as 1.92, and if you go back and see our actual rank matrix, it is 3. Okay, now the optimization definition talks about minimizing the error, right? So what is the error over here? It is basically the error is 3 minus 1.92, that's the difference, and mean square error basically gives you, the error factor over there. And actually, like, you do this for all the other components of the matrix, and like, you can get the mean square error. And this keeping this in mind, we have to now kind of find the optimal value in terms of for these two matrices, user factor and the item factor. Okay, now this matrix factorization is also called as alternate least square, ALS. Why that is? So now what we can do is we can fix one particular matrix, say user factor, and then we can work on the item factor, right? And then fix the item factor, and then we can work on the user factor. So since we are kind of alternating this, basically this is called as an alternating square matrix, ALS. And also this implies that you are converting a non-convex function into a convex function, and then kind of fixing this rank matrix. So this is what primarily happens when it comes to the explicit data. And how about for the implicit data? And implicit data, we know that yes, there is no ranking available. It is all about the behavior of the user. So we build a matrix, basically, how many times the user has played that movie, how many times they have downloaded that movie, how many times they have clicked, how much time they have spent on that page, right? This, by making use of this, we create a matrix, and then what we do is we define the preference matrix over here as 1 and 0, and the preference matrix is 1 if the basically the recorded value, what we mean is if the time spent is more than 0, then the preference is 1, and if they're not looked into a movie at all, then there's a kind of a dislike to that. Okay, this is the kind of an assumption. Okay, but in practical that is not the case. Why? Because for various reason, people user may not be downloading or clicking or looking into that, right? and also the other side also is true. If I look into the movie, doesn't mean that I like that, right? So to kind of overcome this, only we kind of introduce the constraint. You remember the definition of the optimization initially we told about minimizing the error, maximizing the accuracy, and also we need to consider the constraint. So here, that is why we bring in the factor confidence, and we add a constraint over here 1 plus, and then a tuning parameter alpha, and then the recorded no, data. Right. So making use of this, we come out with that error minimization value. Right. So as you see, this particular like this is how the the loss is minimized for the implicit data. And now you can imagine like machine learning, or basically in general AI, is purely like it's an optimization problem. And our high school max, whatever we have studied, is really playing a big role in each and every aspect. And I'm sure like this helps you to get a quick understanding about now AI as an optimization problem. Hope you find this talk useful. Thanks for watching.